people really find helpful, so put it in this chart, and this is a common chart. This is actually part of something called the 12-fold method. You don't need to remember that name in any way, shape, or form. You actually don't get to all 12 pieces of the 12-fold method until you start doing combinatorics up in graduate school. Okay, so like way far advanced from what we're doing. But in terms of what we're doing, you can totally put it in terms of this chart. And this chart, the top row here, looks at all the situations or all the formulas when order would matter. And remember what order matters means. This means that if you have something like A, B, C in a list, that is counted as a different situation than if you just rearranged the individual items, okay? So here, if repetition is allowed, this is the situation where you have the exponents. So like n raised to the k, where n here would be the total number of choices per object, k would be how many locations, how many slots in your sequence you have got. Okay. Now, order matters, but repetition not allowed. This one here is your following factorial. Or if n equals k, so if k here equals n, a following factorial is exactly the same as the regular old factorial. So these two guys are actually in the same position. And remember what both the following factorial and the regular factorial did. It started in the first slot, could have any of the n objects. The next one, you can pick any of them except the one you've already picked. So the number of options decreases each time, which means instead of the exponent, where you had all the same choices, here you're decreasing in terms of your choices. Now, order doesn't matter, but repetition not allowed. So down here in order doesn't matter, both of these two guys in this bottom row, this would be where you're building sets. So if you do something like A, B, C, if it's in a proper set, that's exactly the same as if you reordered the individual elements. Okay. Now, we actually did this one sort of backwards. We did sort of a backwards C when we went around these blocks. We actually did this lower right-hand block next in order, and this is where you have n choose k. Okay? And if you remember, we said this one was the same as our following factorial divided by k factorial, or if you preferred the way that statistics guys like to use it, n factorial over k factorial over n minus k factorial. There's two different formulas that you can use. Okay? So that would be this guy. Now, the last one, and this is the one that we talked about last time, was multi-choose. So this is n multi-choose k, and this one turns out to be, you can rewrite it as a formula with respect to n choose k, or really it's add the two guys together, the n and the k together, subtract one because it's one too many, and then select k of those guys. Okay. So that would be the formula, and I gotta admit, this one here, this is one of those things that it's relatively easy to remember it in this format. I mean, you still got to put a little work into remembering it, but this one here, it's a way to clean everything up and make it sort of a quick snapshot. All right, now, with this stuff here, so with this chart, and I'm really wishing that I could like keep that chart up in front of you. So this would be the time of maybe taking like a screenshot or write it down so you have this in front of you. But what you do with this guy is then you start looking to which block you're going to be in. So you're looking to see, does it matter the order in which I select my thing or not? Does it matter if I'm allowed to repeat things or not? And that'll get you to the right block and the right formula. Now, using all that information that we've totally already done, let's go back to the original question that we started off on. Okay? So the original question that we started off on was this thing, you've got a place that sells fruit. I picked a grocery store when I typed it in, but anywhere that sells your fruit here. You then you go in, you decide that you're going to use this, or let's not really use, but take advantage of this discount, this sale, this however they've priced it, that you want to go ahead and select 3 pieces of fruit from their selection. And we said that we arbitrarily here picked 5 types of fruit: apples, pears, bananas, peaches, and oranges. Maybe it's because it's all the fruit they have. Maybe it's because those are the ones that they want to move quickly. Okay? But regardless, when we're going through this one, what should we do when we're trying to select the pieces of fruit? Well, if we want to identify which of those 4 formulas that we would be looking at, the 2 things that we've got to figure out is repetition and order. So typically you look at order first. So think about when you're going to buy something, and I'm assuming that all of you have bought something from a place that sells stuff before, okay? Even if it's not a grocery store. You go in and you buy your stuff. Does it matter the order in which you pick out those 3 pieces of fruit? Yeah, so it would not. So order here, order wouldn't matter. So it doesn't matter. The thing that matters is which pieces of fruit you actually pick. So moving back to our previous slides, I'm going to flip back here. What happens if order doesn't matter, we're options here are only these last 2. So it would only be either the N choose K or the N multi-choose K. Yes, I know their symbols and their names are very similar. The only difference is whether you're allowed repeats or whether you're not allowed repeats. So let's go back to our question. So when we go back to our question here, what do you guys think? According to the information that we're given, are we allowed repeats? In other words, could you select more than one of the same type of fruit here? Yeah, if you saw that sign in a store, I'd say there's nothing on that sign that say you decide for whatever reason you wanted 3 bananas that day. I picked bananas because that was the first one that I saw. You take your 3 bananas up to the store, would you be surprised if when you were getting rung up, whether it was auto thing, self-checkout, or whether it was with a person and they tell you, I'm sorry, this sale is only if you have 3 different types of fruit. Yeah, I would be surprised too. Okay, so this one here, repetition doesn't matter, or it is allowed. Now, if you have order doesn't matter and repetition allowed, which of those 4 formulas are we going to end up getting? I realize it's difficult to type them, or at least some of them. But anybody have a guess which of those formulas we're going to be using? Oh, that is a good way of typing it. Yes, so for this one here, what we would be looking at is we would be looking at 5 multi-choose 3 here. N equals 5 because that's the types of fruit. And 3 because 3 here is the number of fruit that are selected. So all of this to the side, that's our scratch work. Now, if you actually wanted to calculate that integer answer, here's where you have to go and grab the formula. And since you can't see the 2 slides at the same time, let me go ahead and remind us what the formula was. If you have n multi-choose k, you can rewrite this as n plus k. You always add the 2, subtract 1. And then it's n plus k minus 1, choose k. So we went from the multi-choose to the regular old choose. And that's because we actually have a formula for the regular old choose. Which means in this particular case, the easy part, we're going to something choose 3. Anybody got a line on what the number on top is going to be? And I'll actually put the formula here once we have it. 7, looks like 7. Since I can't write a 7 today. So this is 5 plus 3 minus 1. So you've got 5 plus 3 is 8 minus 1. You've got your 7 right there. Now, once you have this written in terms of 7 choose 3, we can totally use the same n choose 3 formula we've done in the past. So that's 3 times 6 times 5. Start with 7, pretend it's a factorial, but stop when you get to 3 factors. And then we'll divide it by 3 factorial. Now, 3 factorial and 6 are exactly the same. So those 2 are going to cancel, which means the answer here is 35. Okay. Makes sense? Kind of okay so far. Notice in terms of the formulas, this is very, very, very similar of if you were doing something with just a straight up n choose k. The only difference is here, you're allowed to repeat the items, and with a straight up n choose k like this one, you're not allowed to repeat the items. Notice, so like a part B, maybe we make this part A, maybe this is part B. What happens if you can't repeat? So maybe you can't select the same fruit. Maybe you actually did get to where you were trying to buy your, what did we say before, 3 bananas, and the store says, nope, I'm sorry, you really do have to have 3 different types of fruit. So maybe you go back and pick your 3 different types of fruit. If you can't repeat types of fruit, in that case, your answer would simply be 5, choose 3. And the question, of course, is, what do you guys think? If you aren't allowed to double up and repeat pieces of fruit in your order here, do you think you're going to have more selections or fewer selections in Part B? Should have a lot less. In other words, you should now, in this Part B that's sort of over to the side, you should have ones where you've eliminated those 3 bananas, or 2 apples and 1 pear, or 2 oranges and 1 peach. Okay? So here, if we calculate the 5, choose 3, which would be the situation where you're not allowed to repeat types of fruit in your selection, this would be 5 times 4 times 3. On the bottom is 3 factorial. So 5 times 4 times 3. And I'll write out 3 factorial because we don't have a 6 on top. The 2 and the 4 would cancel. The 3 and the 3 would cancel. So this would be 10. So notice when you are allowed to do repeats, or in this case, select more than one type of the same fruit, we've got more than, what was that, 3.5 times as many options. Okay. So there's definitely a difference here, and this multi-choose is typically much larger. It's still a 2-digit number, but it's a fair amount larger here. Okay. Questions make sense? Kind of feeling a little bit okay. All right, seeing no questions come in, that's the last example on this topic. So the next thing that I've got for us, so this is the only issue of sharing your entire desktop, is you'll get to see all of this. The stuff I normally hide from you. Oh well. So the next thing we've got is very much the wrap up. Another example in order to test. You mean for project 2? Okay. Is that something that you guys want to talk about right now, or is that something that you're looking for just like an extra one posted? So which one did I give you? Did I give you n equals 2? I think I did. I think that was the little picture. 2? Okay. Here, just a second. So what I assumed, I don't have this up, so let me pull this up. So what I assumed by giving you guys n equals 2 was that you guys could figure out n equals 1 on your own, because n equals 1 looks like this. So this is for project 2. Anybody have a guess what the answer should be for n equals 1? And remember, you can only move left to right or top to bottom. Okay. So you've got one example that goes like this, and you've got one example that would be like this. Okay. So yeah, the answer here would be 2. Okay. So I assumed that you guys could deal with that one on your own. I gave you n equals 2, and if you get n equals 1, n equals 2, and n equals 3, you probably are going to be fine. In terms of n equals 3, I won't do the whole one for you, but I'll do a couple of them. I actually have to go out to 3. So there's the extreme cases. And then the one that's similar to that, but on the other side. So down and then over. But then you've also got the ones like this. And I would actually recommend drawing each of these out. It's a pain in the butt to do, but it means you don't get confused about where the path is on the new example. Okay? So for example, here maybe you go out 2, and then if you go out 2, you have several options of where you can go down. Okay, so you can go down 1, and then go over, and then you're forced. Everything else has to be the same. And now I'm going to do what I told you I wouldn't recommend. You could also go down here, and once you've gone down 2, you're forced for the last move because you can't do anything but go all the way down to your finish line. And then you could also go all the way to the bottom and go over there. Okay? So that's a sort of a strategic way to try to get all of your paths. So this here you can do for all of the n equals 3 guys. Start off and have this very first one go straight over, so left to right. And then it's either go all 3, go 2, go 1, go 0. And then each of those, after you do the first move of making your arrow go as however far you want, then you've got each of these cases going down. Okay? Because remember, you can't go down and then go back up. It's only go left to right or go top to bottom, or top down, I guess I should say. Okay? So that would be the strategy of how to build to n equals 3. I wouldn't bother necessarily with n equals 4 unless you've got a bunch of spare time on your hands, but you can do the same strategy for any n you want. Okay, so that can be some way that you can test it. Right, so we were at this one. All right, so this was the last little bit of wrap-up counting that we didn't get to last time, and it actually covers 2 principles. We've already talked about one of them, but I didn't give you the name, or at least I don't think I gave you the name. It was called inclusion-exclusion, and we actually covered it when we were back with sets. So I wanted to do really one example on inclusion-exclusion and show you how it would now be applied to counting techniques. Because remember, what did we see when we first started looking at counting? We said counting was essentially you have some sort of set, and you're finding the cardinality of that set. Okay? The second thing is something called the Pigeonhole Principle, which is why the little graphic is what it is. So the majority of the questions in here are really going to be dealing with this Pigeonhole Principle. And I've only got a handful of examples here total. All right. So the first example here is, well, this is a case where I didn't actually insert a poll everywhere question because I did not think that the other one would necessarily work, or at least I didn't check. Okay. So I actually went ahead and threw this one up on a poll everywhere question, so I'll go ahead and let you guys go and find it. Let me write this up to the side, top right here, what the URL is. I don't think I can actually share 2 monitors at the same time right now. But while you were thinking about that, let us actually do some of the preliminary work. Okay. And then you guys can take a guess on what you think the final answer might be. So if we're looking at only the integers between 1 and 100, so include 1, include 100, so integers 1 through 100 would be better. And we want to know if they're divisible by either 5 or 7. So if you wanted to know if they were divisible just by 5, any guesses what you would do? You've got your numbers from 1 to 100, and you want to know how many of them are divisible by 5. Any guesses what you would do? Yeah, you would just divide your 100 by 5. Now watch out, if you still have 100 numbers and it's not specifically the integers 1 through 5, the integers 1 through 100, you got to be a little bit more sneaky about it. But if you just have the integers 1 through 100, you just divide them by 5, and hopefully you're all thinking that number is 20. Now, any guesses what you would do if you wanted to figure out how many of these integers are divisible by 7? Don't overthink it. What should we do if we want to get divisible by 7? Or multiples of 7, if you will. Not quite. Unless you mistyped it slightly. So this one here, you actually do the exact same thing. almost. So you would still divide by 7, but if you divide by 7 of 100, it's some decimal. And then decimal is actually 14.28, and it keeps going, and we don't care about any of those decimals. Now, you have to have an actual whole number. You're not allowed to have a specific a decimal answer or part of a number to be a number that's divisible by 7. So yeah, what you're going to do is exactly what one of you suggest, is we are in fact going to take the floor of this, or we're going to round down. In other words, you truncate the decimal, okay? We'll actually talk about floors and ceilings in a little bit. I'll go ahead and put the notation in, but what we're going to do here is we're just going to truncate off that decimal, okay? So if you haven't seen a floor before, don't worry about the symbols. We'll talk about it in a sec, okay? Now, so once we have that there are 20 numbers between 1 and 100 that are divisible by 5, and 14 numbers between 1 and 100 that are divisible by 7, now the question, of course, is, all right, we didn't care really how many numbers were divisible just by 5 or just by 7. We care about the numbers that are divisible by 5 or 7. So what do we do with those two numbers? Any guesses? Or should we calculate something before we actually figure out the final answer? It is all about the setup for this question. Well, if you need to be divisible by 5 or 7, you got to make sure you grab all the numbers that are divisible by 5. You got to make sure you grab all the numbers that are divisible by 7. But I'm going to claim if you just straight add them together, there's something a little bit funky. So remember, this is the point where you guys have got some guesses. So about half of you have made a guess before. So before I give you the final answer, go see if you can't make a guess. Okay? Those of you who haven't done it. Oh, it looks like mostly guesses. Excellent. All right. So while you guys, or at least while half of you were making a guess, I wrote this out in terms of sets. So I went ahead and defined a set A and said, hey, these are all of the numbers that are between 1 and 100 that are multiples of 5 or are divisible by 5, and we already counted, there were 20 of them. I went ahead and defined the set B to be all of the numbers between 1 and 100 that are multiples of 7 or are divisible by 7, and we found there were 14 of them. Which means this thing that we're trying to find here, the divisible by 5 or 7, is exactly the same thing as saying, hey, we want to find the cardinality of the union of those two sets. Now, we've totally done this before. And what did we find in the past? Well, you add the two cardinalities of the two sets together. So throw in all of those objects from the two sets, but you're typically going to be overcounting. So then you need to subtract off the cardinality of the intersection. So if we plug this in, this would be 20 plus 14 minus something. So this is where you have to figure out what that something is. Well, if we look at the intersection is when you have both of these two conditions. So this means you have to have some number that is divisible by both 5 and 7. Well, if you're divisible by both 5 as well as 7, this means you are divisible by your 35. which means if you're trying to figure out how many guys are divisible by 35, you want to do that same thing we did before, which says divide your 100 by 35 and see what's going on, okay? So what happens? If we actually go ahead and do 100 divided by 35, anybody happen to get what that number is? I realize it will be a decimal, but if you truncate the decimal off, anybody get what that number is? Or if you want to give me the decimal, that works too. Yep. Once you go ahead and truncate off the decimal parts, it would turn out to be 2. So this actually, in terms of decimals, was 2.87857 and a whole bunch more. So same thing as before. If you get an actual decimal, and you will for any sort of sevens, because 100 is not divisible by 7, you're going to get a decimal. So we chopped off all the decimals, and notice here, it didn't matter that was a 0.8 closer to 3 or a 0.2 closer to the 14. We don't care as long as there's any decimals. We're just going to truncate and get to the straight up 14 or 2, which means here we'll go ahead and plug in that 2. And then once we do all of the arithmetic, what answer should we end up getting? To go ahead and show you the work. Yep, so you just add them together, so this final answer should be 32. Watch out, inclusion-exclusion, and this is an example of inclusion-exclusion, does not require these individual cases that you build to be mutually exclusive. Mutually exclusive meaning no overlap. When we've been doing counting in all of the previous times for counting, one of the things that we did is we were very careful, or we tried to be careful, with our cases, if we had cases, that there was no overlap between the cases. But it turns out there's not all situations where you actually can have a no overlap situation between your different cases that you're dealing with. And when you can't guarantee the no overlap, this is where inclusion-exclusion comes in, because it says add everything like you want to, but then subtract any of the bits that are the overlapping parts. Okay? So this is an example where we wanted to count up how many whatevers, and we had to go back to this union formula or cardinality of the union. Now, just to remind ourselves, inclusion-exclusion, this is exactly what we just said. We broke everything up into cases, but there's no guarantee that, so here you typically have overlap. So overlap typically exists, because otherwise you wouldn't use inclusion-exclusion. So then when you're trying to actually do the count how many objects there are, you do this thing where you've got what? You've got the cardinality of all these unions, and we saw previously that that was where we said, hey, we just add up all the individual cardinalities, and you keep on going until you have whatever the last one is. Maybe this last one is n. So maybe here we have an n. Okay. Then you subtract, and you subtract all the 2 element intersections. So you keep on going, all of the 2 element intersections, all 2 element intersections. And then you add all of your 3 element intersections. Then you subtract all of your 4 element intersections. I am not listing all of these out. And you keep on going until you actually, at the very, very end, it's either going to be plus or minus depending how many sets you actually have. And this would be where you either add or subtract the very last possible intersection, which is where you intersect all of your sets together. Okay? And we looked at this formula previously. This was like one of the last formulas that we looked at when we were in our section dealing with sets. But notice here, because you can rephrase or rewrite all of our counting problems in terms of sets, this is something that you can then now use here. When it's back in sets, it's often, it's not always called the inclusion-exclusion principle. When you're up and counting, this guy is called inclusion-exclusion because you're including things, then you're excluding things, then you're including things, and you're excluding things, and so forth. Okay. In our situations, you're probably not going to have tons and tons of these guys. Okay. As in tons and tons of sets. You wouldn't have lots of sets going out. But that's it in terms of inclusion, exclusion. Okay. Questions or kind of make sense so far? All right. I'm not seeing any questions come through, so I'm going to go ahead and move on to our next thing, which is actually the pigeonhole principle. Okay. So first of all, let's talk about what it is, then we'll see how it gets interpreted, and then we'll do a couple of examples. So the actual pigeonhole principle is defined in terms of pigeons and pigeonholes. It actually was, historically speaking, created by, I forget the guy's name, but he had homing pigeons. I believe it was late 1800s, if I remember correctly. And he was literally watching his little homing pigeons or whatever type of pigeons he actually had. I think it was homing pigeons. And they would fly into their nest where the little pigeons slept for the night. And he noticed that, oh, this is something that could happen with my pigeons. And then it got developed into a mathematical thing. So here's the situation. You've got a certain number of pigeons, so n pigeons, and they have m pigeonholes that they would go and nest in or sleep in. Okay? And suppose the number of pigeonholes is actually less than the number of pigeons. Then, this is all the pigeonhole principle says, then at least one pigeonhole has got to contain more than one pigeon. It's literally all it says. It's one of those, once you think about it, you're like, how is this not something that's everybody knows? Okay, but this is the official thing. Now, let's see what this would mean in terms of an example. And in this case, I went ahead and grabbed us actual numbers for the n and the m. That way it's easier to see. Okay? You can totally do a little scratch work to show what this would look like. So if we have 7 pigeonholes, suppose we have 1, 2, 3, 4, 5, 6, and 7 pigeonholes. So these little space holders right here, I'm going to assume are the pigeonholes. Now, suppose your pigeons start coming in and they decide they want to sit in the different pigeonholes. Maybe they're tired, whatever they're doing. Okay? Well, what happens? There's a couple of different scenarios. Maybe the first pigeon comes in and it gets into the first pigeonhole. Maybe the second pigeon comes in and it doesn't like that pigeon, so it goes into a pigeonhole a little bit further on down. Maybe the third pigeon comes in and it really likes the first pigeon, or it just doesn't care, and it comes to the first available pigeonhole. So maybe they're flying in from this direction. Maybe a fourth pigeon comes in and he gets into the very last pigeonhole. Maybe the next pigeon flies in and gets into the next to last pigeonhole. Maybe the, what is this, we're at 5, 6 pigeon comes in and gets the first pigeonhole that's left, and the 7th pigeonhole comes in and flies in and gets into the remaining pigeonhole. Okay? What happens to pigeon number 8? What has to happen from this diagram for pigeon number 8? Because remember, we have 8 pigeons and 7 pigeonholes. What do you guys think? Don't overthink it. What happens? A pigeon comes in. He tries to find a place to roost. He tries to find a little pigeonhole for himself to do whatever he wants to in there. And they are all filled up. So if he's going to go into a pigeonhole, what happens? He's got a double bunk. Bam. Maybe he shares with that third guy. Huh? Now, this is one extreme case. Maybe you think this is the best case scenario. Maybe you consider this the worst case scenario, but this is one of the extreme cases. This is where the pigeons have distributed themselves as far as possible or as evenly as possible, okay? So you try to have no double bunks and you end up you had to have somebody. Now, there's another extreme case, and it's the opposite version. So this is the other extreme case. Anybody have a guess what the other extreme case is while I'm putting in these 7 pigeonholes? Yep, so that's the other extreme case. Maybe all 8 of your pigeons, for whatever reason, go in and all try to get into that one pigeonhole. Now, I don't know which of these two cases you consider the best case or the worst case scenario. If I was this little pigeon right here, I would definitely be considering this top case the best case scenario because I got my own little pigeonhole. And this one where I'm crammed in, perhaps have a foot in my face, the worst case scenario. But depending on what you're trying to do, one of these would be considered like a best case versus worst case. But in both of these two extreme cases, do we actually have a pigeonhole, at least one of them, maybe only one of them, that contains two or more of the pigeons? What do you think? Do we meet that criteria in both of our two extreme cases? Yeah, and the answer is yes. In the first one, there was only one pigeonhole that met that criteria, and they just barely met it. You had only two pigeons in exactly one pigeonhole. In the second one, we also had only one pigeonhole that had more than two pigeons. It had all the pigeons. It had way more than two pigeons. But again, there was just one pigeonhole that met the criteria. Okay? Now, somewhere in the middle, so not an extreme case, well, what can happen with not an extreme case? Maybe you have something like this. What is that, 6, 7? Maybe you have something like this, throw in the 8 pigeons across the 7 pigeonholes. Maybe you've got some of them that have double bunked. Maybe you've got some of them that are single. Here, we've got more than one pigeonhole that has 2 or more pigeons. But notice, the only thing you have to check to guarantee this works in all cases are you've got your two extremes. And really, the only one that you actually have to check to make sure that the pigeonhole principle works is this top one. Because why? The only way you could break your pigeonhole principle is if you could spread out all of your pigeons on these pigeonholes such that you could find where there was no pigeonholes with 2 pigeons in it. And this is the only situation where you even have a hope that that would happen. So this is the extreme case or the worst case where you might actually break the pigeonhole principle. Okay? So this was an illustration of pigeonhole principle with respect of actually using the words pigeons and pigeonholes in the setup of the question. Most of the time, you're not dealing with pigeons or pigeonholes as actual birds and actual physical things are going to. Most of the time, you tag some entity in your example as the pigeons or as the pigeonholes. So all the rest of the examples are like that. Okay? So before we move on to the other examples, does this illustration make sense so far? Questions so far? All right, I'm not seeing any questions, so let us look at the next example. Next example is not one that was trying to trick you in any way, shape, or form. So it goes as follows. It says, suppose you have a group of 8 people doing whatever they're doing. Typically, in a counting question, they'll often say a group of 8 people on a committee or on a sports team. So picture these 8 people doing whatever it is they're doing. Okay? Can we guarantee that at least 2 of these 8 people had to be born on the same day of the week? So like Monday, Tuesday, Wednesday, etc. What do you guys think? You think it's possible that in a group of 8 people, you could guarantee that at least 2 of them, maybe more than 2, maybe exactly 2 of them, but they were born on, say, both a Tuesday? The assumption here is that you could figure out what day of the week they were all born on. This is actually a pretty classic question. The other classic question that is typically asked, and I'm not going to go over it, but is typically asked at this point is, suppose you have a class of 35 students. Can you guarantee that at least 2 of the students were born on the same day of the month? So in that case, you're looking at days, like are they both born on the 2nd? It's the same type of question. Well, let's look to see what you would have to do. So the buzzword here to look for is, can we guarantee, okay, it's not really a buzzword because there's going to be several words, that at least 2 people were born on the same day of the week. Those are the key things that tell you we're going to be looking at pigeonhole principle. Now, is this the only way to do it? In this particular question, yeah, this is probably the only way to actually answer this question. In other situations, are there other ways to answer them? Possibly, sometimes, definitely yes, but this guarantee and the not being really specific of knowing which two people were born on the same day of the week, that's the pigeonhole principle. Because the pigeonhole principle does not tell you the exact count. It doesn't tell you who shared, in this case, a birthday on the same day of the week. All it does is it guarantees existence. It says, yep, you have to have that two, we don't know which two, but at least two of your people were born on the same day of the week. So in order to apply pigeonhole principle, you have to do three things. The first two things are identify who will be tagged as your pigeons and who would be tagged as your pigeonholes. So in this particular situation, anybody have a guess of who you would tag as your pigeons and who you would tag as your pigeonholes? Any guesses? Well, if you read through this question, what's something key that you have to worry about? I'm going to switch over to a highlighter right here. So two key pieces. Ooh, not the question I asked, but totally going to come into play in just a second. So I'm assuming that you were looking at people and days of the week. So if you look at your people and your days of the week, the question here, of course, is which one should be our pigeons and which one should be our pigeonholes, okay? So the way to distinguish between them is the pigeonholes, and let me go back. The pigeonholes were what? These were set things, and the pigeons got to sit in whichever pigeonhole they wanted to. So in terms of a problem that doesn't have designated pigeons and pigeonholes, where you have to decide who's going to mimic the behavior of the pigeon and who's going to mimic the behavior of the pigeonholes, the guys that are going to mimic the behavior of the pigeonholes are the ones where you don't necessarily know who they match to right now. And the guys that mimic the pigeonholes are the ones that you know exactly what's going on. So with our group of 8 people, we don't necessarily know when they were born. We could potentially figure it out if we ask them, but we don't necessarily know at the start of this question when these guys were born. But what do we know about days of the week? Do we know what days of the week there are? Are these guys fixed, in other words? Before the start of the problem, if somebody asked you about days of the week, could you tell them what was going on with those guys? With the days of the week, that is. Yeah. So that means in terms of pigeonholes, the days of the week are going to be your pigeonholes, and your people are going to be your pigeons. This now allows you to do the little scratch work, same scratch work that we did in the previous example where we had pigeons and pigeonholes, except now you can say something like maybe this is Sunday, maybe this guy represents Monday, maybe this is Tuesday, maybe this is Wednesday, maybe this is Thursday, maybe this is Friday, maybe this is Saturday. Pretend there was an A. Okay. So then when you have your 8 people, you can do the same sort of extreme thing that you did before of looking at extreme cases. And you always, if you're trying to do this scratch work where you just do one case, you always try to show that the pigeonhole principle doesn't work. In other words, you can make it so that none of these guys have 2 people that were born on the same day. So for example, person number 1, maybe person number 1 was born on a Monday. Maybe person number 2 was born on a Tuesday. Maybe person number 3 was born on a Thursday. Maybe person number 4 was born on a Sunday. Maybe person number 5 was born on a Saturday. Maybe person number 6 was born on a Friday. And if you're really, really trying to break it, person number 7 that you interview to find out when they were born, when would person number 7 have to be born if this was like a worst case scenario where the pigeonhole principle might break? That person number 7 would have to be born on which day? If the pigeonhole principle might break. In other words, it's not applicable. Well, maybe he gets born on that one. So say you interviewed 7 out of your 8 people. You get the final answer at the 7-person mark that all 7 people were born on a different day of the week. Now, what happens with your 8th person when you interview them? Well, that 8th person has to be what? If we look at days of the week, are there more than 7 days of the week? Hopefully you're all thinking to yourself, no. So that 8th person, when it comes in, maybe he's born on a Sunday, or a Monday, Tuesday, Wednesday, Thursday, Friday, or Saturday. It doesn't matter which day of the week he's born on. Whatever day of the week he's born on, somebody else that we've already interviewed was also born on that same day. So this means we've doubled up. Again, it doesn't tell us which day of the week we have 2 people on, but we know that if this is the most extreme case where you've spread out the days of the week people were born on to be the worst possible situation, trying to break your pigeonhole principle, and it still didn't break, that does tell you the pigeonhole principle here is applicable, and this will give you this situation here that, hey, we know that we're going to be able to guarantee at least 2 people were born on the same day of the week. Now, specifics. You find your N. N is the number of pigeons, so in our case we had N equals 8. M was the number of pigeonholes, so we got that M equals 7. And you don't even have to do scratch work. The only thing you really have to do is once you've established who your pigeons are and who your pigeonholes are, you just compare these 2 numbers, the N and the M. And if you want to write this up, this would be what the answer would actually look like. I thought that was going to fly up a little higher, which is why I scrunched this all to this top. So since we actually got the number of people, and we probably should have identified, hey, people were representing our pigeons and there were 8 people, and days of the week were representing our pigeonholes and there were 7 days of the week. Since there were more pigeons, or there were more people than days of the week, if we apply the pigeonhole principle, what happens? There must be at least 2 people, maybe more, maybe exactly 2 people that had to be born on the same day of the week. Notice it doesn't tell you which day of the week, and it doesn't tell you which people or exactly how many people, just that at least 2 or more people. Okay. Questions? Make sense? Kind of feeling okay. That's literally it in terms of pigeonhole principle. All right, well, let us do another example that's not quite this straightforward. So the next example I've got for us is actually a math example. So suppose you have the following. Suppose you have a set of 12 integers, integers 1 through 12, and you have selected 7 integers from this set of 12. Who knows why? It just happened. Okay? So you selected 12 integers from this set, selected 7 integers from the set of 12. Then what we want to do is we want to check to see at least one pair of these 7 integers will sum up to 13. So that is the question. Can we actually always guarantee that regardless of which 7 integers are actually selected from this set of 12, that there's always going to be at least one pair of those 7 integers is going to add up to 13? Which seems crazy at first glance, maybe. So key things, this is going to be a pigeonhole principle. Because you've got here the at least, this is also that there's a guarantee. It doesn't tell you which pairs. And so that at least right there and the one pair tells you that you're looking at 2 integers. And then it tells you what some criteria is. So of course the question here is, how do we actually figure out who's the pigeons and who's the pigeonholes? Now, anybody have a guess who the pigeons are and who the pigeonholes are? This one's a little bit more tricky. I don't think I have anything else that flies in on this slide. So, in terms of these guys, the thing that you are checking, the thing that could potentially change depending on what happens, are the integers. And these are the ones that are selected from your set. So those guys would potentially be your pigeons. Now, if you've selected 7 integers, that would mean we have a grand total of 7 pigeons. And we'll see if that works. Because what happens if you guess wrong, you'll just go back and we'll see if there's an alternative way. Okay. Now, what we want to do is we want to check to see pairs of integers. Well, we have a grand total of 12 integers that we're looking at, and we're trying to grab pairs of them. So one of the things to do here is actually look at what pairs of integers in 1 through 12 actually do sum to 13. So for example, if you take the integers 1 and 12, what happens? 1 plus 12 is 13. So if we actually pick two integers here, if we pick both of those guys, that would be a pair that would sum to 13. Now, off the top of my head, do I know how many pairs sum to 13? We'll figure it out, okay? So one pair is 1 and 12. Anybody have a guess what another pair might be? And I'm going to put all of them here below these little scratchwork holders. Well, you've got what? You've got 2 and 11. You've got 3 and 10. So remember, these are all the two numbers that will sum together to get 13. And I didn't worry about order, which is why I put them in terms of a set. Because if you pick 10 first, and then you pick 3, or you pick 3 first and then 10, at the end of the day, we're just looking. Yep, 4 and 9. Are there any other possibilities? What, 5 and 8, right? Are there any other possibilities? It looks like also 6 and 7. Let's check, have I missed any? And this part here is really critical. You want to make sure that your count of how many pigeons and pigeonholes that you have is accurate. So this is why you'd, in this case, where we're actually building what will become our pigeonholes, we want to be very careful to make sure we haven't missed any, because the count here is going to be important, because it's so close to the number of pigeons. If they're really far apart, it's easier to tell. So pigeonholes would be our what? These would be our pairs of numbers. So pairs of integers that sum to 13. And how many of those pairs of numbers did we actually end up getting? Did anybody count up how many of those pairs we got? It looks like I'm getting 6. Are you guys getting 6? All right. Now, once you're at this stage, you can visually just compare how many pigeons. We said there were 7 integers were our pigeons. How many pigeonholes? We said that there were 6 pairs of numbers that summed up to 13. So these pigeonholes, fewer than the pigeons, which means, yes, it should work. So by the pigeonhole principle, since n, which is 7, is greater than m, which is 6, we get that, and this is where you basically repeat the thing that you're told at top, that at least one pair of the chosen or selected integers will add up to or will sum to 13. Okay. Now, let's see if that actually holds up in the scratch work. Worst case scenario, maybe in this first one you pick a 1, and I'll actually write down what numbers we pick. In the second one, maybe you pick an 11. In the third one block, maybe the third letter you picked was a 3. You guys tell me. Maybe next we pick, what number would you guys like us to pick next? We're going to try to pick 7 integers between 1 and 12. What's another number we could pick next? And remember, we're trying to break pigeonhole principle right now. So what's a number you guys would like me to pick next? Don't overthink it. You have lots of possibilities. Sure, 9 would work. What's another number you guys would like me to pick? Remember, we need to pick 7 of them, so we got 3 more numbers to pick. So what's another number? You got fewer options now. Yep, 5. What's another number we could pick? Remember, we need to pick 2 more numbers. Anybody got one you guys want me to pick? And remember, we're trying to break pigeonhole principle, so 7 would be a really good number to pick. Now, at this point, we've picked 6 numbers from the integers 1 through 12. We semi-randomly selected them. And for each of them, it doesn't matter which pair of these numbers you pick, none of them are going to sum up to 13. But as soon as you pick that 7th integer, and one of you said 4, because we picked the 4, that one is going to match with the 9 we already selected, and here would be our pair of integers that actually sum up to 13. So it does turn out that this totally works, and the reason it works is because we were able to grab an appropriate selection for who the pigeons and who the pigeons' holes were, and since the number of pigeonholes was fewer, it didn't matter how much we tried to break it, you were always guaranteed at least one pair of numbers that sum to 13. Now, if you did a different random selection of integers, maybe you didn't actually pick one integer from each pair. Maybe you ended up with 2 pairs of integers that would sum up to 13, but that's not the case where you're trying to break pigeonhole principle right here. Okay? So in scratch work, always think to your head, I'm trying to break it. I'm trying to break the pigeonhole principle. I'm trying to make it so I don't get those 2 numbers or those 2 pigeons all in the same thing. Okay? Questions make sense, kind of feeling okay-ish. Okay, well, in that case, let me throw this next example to you guys. So I went ahead and just activated it up on Poll Everywhere. I don't have it inserted in these slides right now because, again, I only did it that one time earlier today, so I'll know in the future I can put the slides in here, but it didn't make it for this next example. But this actually is the example, so if you're on Poll Everywhere, you'll see the same one, and let me write the URL at the top. And I'm going to let you guys guess, and I'll go ahead and read it out as soon as I finish copying down the URL. So this one here is a situation, I'm not going to lie, I think about this almost every time I go and try to pull socks out of a laundry basket. So here, what happens? Suppose you've got a pair of socks that has ducks on them. Suppose you've got 3 pairs of blue socks that all look exactly the same, 2 pairs of green socks that all the socks look exactly the same, 4 pairs of white socks and 2 pairs of red socks, and they're all mixed together. I totally picture a laundry basket in my head, but I actually typed drawer when I typed up the question. So here's the question. You would like to have matching pair of socks. So you're not like my husband, who is very happy to have not matching socks. You would actually, for whatever reason, want your matching socks. I personally prefer matching socks. It's a pet peeve of mine. But anyway, you want the matching socks. What's the fewest number of socks that you would need to pick to guarantee a matching pair of socks? Now, here is the assumption. The assumption is that you don't necessarily could see the socks that you're choosing at the same time. So maybe this is like the middle of the night. You didn't bother to turn on the light. You still need to grab your matching pair of socks. You know you're going to select a certain number of socks, and then you'll go out in like the hallway and look at them in the light. Maybe you're trying not to wake up somebody else in the room. Who knows? Okay. But for whatever reason, you can't visibly just go in and select the 2 socks that match. Okay. So that's the background. So I see about half of you have made a selection so far. I'll give you guys a little bit of time to see about the rest of you getting a guess for this as well. What's the key thing here? If you want to identify pigeons versus pigeonholes, in this particular case, who would you be tagging as your pigeons? Anybody have a guess on that? Everything is going to be related to socks. So in order to do this question, you would have had to figure out your pigeons versus pigeonholes, even if in your head you didn't tag them that way. Yeah, that would be a good thing. So the actual pigeons would be the socks that you select. So socks selected or grabbed or, as you wrote, drawn. Okay, so I'll just write sock colors, but yeah, sock types would be a good one too. So pigeonholes would be your different options of your different types of socks. So let's read out what we got. We've got here what? We've got socks with ducks, and all the other ones are colors. So actually, types of socks are probably better, because ducks isn't a color. We had blue socks, We had green socks. We had, was it white? And we had red. Do a quick check. Did I grab all the different types of socks? Did I miss any? I think I got them all. So assuming that those are all the types of socks, how many types of socks did we have? We had 5. Now, no lies, this is the standard way of writing these type of questions. However, it can be confusing if you don't pay attention to what's going on with the pigeonhole principle. So this is definitely a pigeonhole principle, and that is because of this guarantee word. So this is saying, does it exist? And if you look about existence, that's going to be looking at our pigeonhole principle. Okay? So that would be how you would determine that this is a pigeonhole principle question. Now, this one is different than the previous pigeonhole principle questions. The previous ones just said, basically, does this work or not? And it's essentially a yes-no question, almost like a true-false question. Yes, it's true that happens. No, it's false. That can never happen. Okay? But this is different. We're actually going to get a numerical answer here. So if you have pigeons and you have pigeonholes, how many pigeons, how many socks would you have to select in order to guarantee a matching pair? Well, what do we need? According to the pigeonhole principle, we need n to be bigger than m. So if you did it without scratch work, you would just look at what? You would look at the smallest value, the smallest integer for n that's bigger than 5. No lies. I think it's easiest to go ahead and put it into scratch work. So you look at your worst case scenario. Suppose the first sock you pick has ducks on it. Okay, not helpful. We know it's one sock. Suppose the second sock you pick is green. They don't match. Suppose the third sock you pick is white, fourth is blue, fifth is red, and so there is the possibility, in other words, the worst case scenario is you could pick 5 socks and they're all 5 different types of socks. They're all 5 non-matching socks, which means the fewest number of socks that you're going to pick to always guarantee you've got at least one matching pair is that one extra sock. So this one here says what? This would tell you that your n, your number of socks selected, would need to be that whatever the number of pigeonholes were, so types of socks plus 1. Make sense? Feeling kind of okay-ish. Seeing no questions from you guys, I'm going to assume okay-ish. Please note, if you're not in the worst case scenario, the first 2 socks you pick could actually be a matching pair, and this is why we have this word guarantee. That's regardless of how you've chosen the socks, which ones your hands actually touched. In all of those situations, best case to worst case, you're always guaranteed these matching pairs. And notice what the extra pieces of information were here. The fact that you had 3 pairs of identical blue socks, or 2 pairs of green socks, or 4 pairs of white socks, that didn't matter. As long as you had at least 2 socks of each type, which everybody had at least 1 pair, at least 2 individual socks of each type, you were good to go here. All right. So I'm going to move on to the next thing, and the next thing is actually still pigeonhole principle, but it's called the extended pigeonhole principle, and it's what happens if you have lots more pigeons than pigeonholes. So same setup, you have n pigeons are assigned to m pigeonholes, but now this relationship is the number of pigeons is a multiple of the number of pigeonholes. This is not the way that most books write it. I went ahead and put the A in here just to indicate this is a multiple of. Then it turns out that at least one pigeonhole is going to have to contain A, that multiple, or more pigeons. Now here's what lots of people do, or most books do. They'll actually, instead of writing this number A here, up top they just say N is bigger than M. Notice it's still true, A could be 1 or bigger, so they don't put this in here. And then they say here that at least one pigeonhole contains this guy, n divided by m, and then you take the ceiling, Or other books write the other version of the formula, which is where you use the floor, n minus 1 divided by m, take the floor and plus 1. It turns out these formulas are identical. Now, this is the thing I don't know. How many of you know what floor and ceiling are? In other words, can I go forward and just have an example dealing with this? Or should I take a brief aside here and explain what those two symbols mean? Is what I'm trying to figure out. Okay, that works. I normally do have to do that anyway, so no worries. So if you have a ceiling, both of these, both the floor is down here, and the ceiling's up here. Both the floor and the ceiling are ways to get rid of a decimal and create an integer. So the ceiling looks like this. And what it does is you always round up to the next integer, and that is only if you don't already have an integer. The floor, wow, not flooring. There is nothing after the R. Just a second, we will try to erase that. That's super embarrassing. All right. So floor is this guy. This is also known as the integer part, if you ever looked this up. And this one you truncate. So truncate, so in other words, you round down the previous integer. Okay? So it's easiest to see this by way of examples. I don't think I have anything else on this page. So for example, suppose we look at 6.1. And then we'll do some extra examples down here. 5.9, 5.9. And then what happens if you actually have an integer? Ah, that symbol is wrong. I'm just going to scratch it out. All right, so if we look at the ceiling of 6.1, this one here, what? It always rounds up to the next integer regardless of rounding rules. So you throw all those rounding rules you might have remembered from previous math classes out. Ceiling is always round up. So 6.1 would round up to the next integer, which is 7. Okay. Now, the floor is you always just truncate off the decimal. So here you've got 6.1. If you just chop off the decimal, this would be 6. Okay. So it's two different ways of getting an integer from your given decimal. Now, if we do this with this other example, this one is 5.9. If you take the ceiling of 5.9, what happens? Anybody spot what number we're going to get to? I'm going to let you guys answer these next ones. So the ceiling of 5.9 is, don't overthink it. You're all overthinking it. So ceiling did what? You're going to round up to the next integer. So what's the next integer that is bigger than 5.9? What are we going to round up to? Yeah, you round up to 6. Now what happens if we take that exact same, what in the, we've got this, come on little pen. What if you have that same decimal, 5.9, and you take the floor of it, also known as the integer part, also known as you're just going to round down to the next integer. So what would be the answer for this floor of 5.9? Don't overthink it. Yep, so this one would round down to 5. Now, the only thing that's actually a trick question is notice in both of these cases, it didn't matter if your decimal was really close, really big, or really small, you do the same procedure in both situations. So over here, last one is what happens if you happen to have an integer. If you happen to have an integer, there's no point taking a floor or a ceiling, except notice over here in this formula, it's totally possible that when you divide n by m or n minus 1 by m in either of those two cases, you could actually end up with an integer inside your floor or ceiling formula. So you got to know what to do if that happens. Any guesses what the floor or the ceiling would be if you have an integer on the inside? Don't overthink it. So I guess here's a better question. The point of the floor and the ceiling is to get you to an integer. Are you already at an integer with 4? So down here, are we already dealing with an integer? Well, the answer is yes. So it turns out the floor and the ceiling have no change if you start off with an integer on the inside. Okay? So that's a crash course on dealing with floor and ceiling. In terms of the extended pigeonhole principle, it's just dealing with multiples. And I've got an example prepped up on the very next slide. So let's look at an example. So suppose you've got this guy right here, and I'm going to work half the problem for you guys and then let you guys work the second half of the problem, okay? Or I guess interpret would be the better way of saying it. So suppose you have this situation. Not going to lie, this semester I went ahead and wrote this example or got this example. I don't think I allowed myself lunch that semester. So vending machine and me were quite buddies. Not this bad, hopefully. I didn't actually count. So suppose there's a vending machine near you or at some point in your past, and this vending machine has 12 snacks in it, whatever they actually are, okay? But there are 12 different snacks that you could buy. And let's face it, not super realistic right now, but suppose they were 50 cents each, okay? I did this on purpose just so it would make the math easier, not because this is a realistic number, okay? Now suppose you ended up spending $35 at the vending machine. Let's hope not all at one time. But suppose you ended up spending $35 at this vending machine. What we want to know here is, what's the guaranteed number of duplicates? In other words, how many of one item are you guaranteed that you must have bought? Okay. Is it possible that you could have only bought one of the 12 snacks at this vending machine? Definitely. But that is one extreme case. The other extreme case is each time you bought a snack, you chose a different snack. And in that sort of extreme case, what's the guaranteed number of duplicates that you're going to have as well? Okay? So let's see what we would do here. And it turns out you can actually deal with this the exact same way that we've dealt with regular old pigeonhole principle. First thing you'd want to do is you'd want to figure out what are your pigeons and what are your pigeonholes. Anybody have a guess on what our pigeons and our pigeonholes are? Remember, pigeons are typically the things that can be put in multiple different places for your pigeonholes. Pigeonholes are the things that are fixed. And this guaranteed, that's the thing that tells you you're dealing with pigeonhole principle. Sometimes trying to do scratch work helps, and then you fill in the specifics later. So here you've got what? You've got 12 snacks. I'm not going to bother writing what type they are. I'm just going to count up to 12. So we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I am definitely regretting putting all of them out there. Okay. Now, once you're at this point, what happens? You could buy a different snack each time, and that would be 12 different snacks. Now, before we get too much further, we need to figure out how many snacks we actually bought. So if you spent a grand total of $35 and it was 50 cents each, any guesses how many snacks you bought in total? Anybody have a guess how many snacks you bought in total? You spent $35. They all cost 50 cents. Don't overthink it. You got it. You bought a grand total of 70 snacks all at once. Hopefully not really all at once, but you bought a grand total of 70 snacks from this vending machine. So I've got 70 little hash marks to put in here. No, thank you. So if we look at this thing, let's see, we have a grand total of 12. I know that 12 times 5 is 60, so I'm going to put 5 in here, 5 in each. Okay. Now, once I finish putting 5 of these hatch marks in each of these slots, we've got 60 total snacks already selected. And notice this is a worst case. Worst case, not that you bought all the same snacks, but worst case that it's spread out. Okay? We've got 10 remaining snacks because we just put in 60 here, and we have a total of 70 up there. So if we spread out the 10 remaining snacks, I'm going to be lazy and just put them here at the beginning. That's 4, 5, 6, 7, 8, 9, and 10. Okay? So notice what we have in this worst case or most spread out approach. We've bought 5 snacks of each of the last 2 types, and we've bought 6 snacks of each of the first 2 types. Okay? So that's the scratch work. Notice 70 total snacks bought, 12 different types of snacks that were potentially bought. And what we want to know is, what's the guaranteed number of duplicates of at least one type of snack that you're going to get? Now, 2 extreme cases is this one that was actually drawn up, or you could do the same thing with the snacks and maybe you bought all 70 of the first type. Okay, those are the 2 extreme cases. So using this information, what do you guys think? How many duplicates are we guaranteed to have in any type of situation? And this one is currently active up on that Poll Everywhere site. So it's got some selections for you. And this allows everybody to get a chance to enter answers here. Oh. Most people had a chance to answer. I'm going to check your guys' responses real quick, which I think you guys can actually see. They're a little bit all over the place, but not really. So the only 2 possible answer choices that we actually have are these 2. And it turns out, no, you were working so good today. It turns out the actual answer here, the guaranteed number of duplicates is that was not what we wanted to do. Stop. Go back. No. Okay, there we go. I guess I'm just too close to the menu down there. Is 6. Now, why 6? From this scratch work, you can actually pull the answer of either 5 or 6 when you spread them out as far as possible. Why would we pick the 6 one as opposed to the 5 one? It's the same reason when we went back to the previous example here, what we were looking at, we were looking for that guaranteed pair. So this was, we're looking for that one that has the most number, not everybody else, but this guaranteed one. So using that same logic, we're looking for one of these guys right here, which have that guaranteed 6 that's going on. Okay? Now, can you also find it another way? Sure. So the other one says that you are looking for, and let me go back to show you the formula, that you are looking for, you've got at least one pigeonhole that contains A or more pigeons, where A is, and I'm going to use the easier formula, N divided by M, and you take the ceiling. Okay? Well, if you look at this formula, so aside, of N divided by M, but the ceiling, N was 70, M was 12, so then you have to figure out what 70 divided by 12 with, and it's like 5 point something. It is, let me check my decimal over here to the side. This is 5.833 repeating. We don't care what that 33 repeating is. What we care is the fact that it's a decimal. So according to the ceiling function, you round up to the next decimal, and that's where you can get 6. And that's based off of the formula, okay? If you're doing the scratch work, you always grab the one that has the most little pieces in it, and that's true only if you spread everybody out as far as possible. So notice, this one here, same idea as the regular old pigeonhole principle, except now it's spread out all the way across, okay? Makes sense? Kind of feeling okay-ish so far. Questions right now? Any questions from you guys? Okay. In that case, that's it in terms of counting. So since we got 2 minutes technically for the end of class, I just want to tell you what we're going to talk about next time, but we'll finish up our new topics here for today. So next time what we're going to talk about is, and I'll go ahead, I think I actually have this where I can show it to you. We're going to start talking about relations next, and we'll do that for the rest of the week. So for this guy right here, in terms of where it's at, it's going to be in the very beginning of Chapter 3, Sections 14 and 15. 14 is going to be all the mechanics, and 15 deals with a special type of relation called an equivalence relation. And these guys are all dealing with special subsets of a cross product. So if you forgot what a cross product is, hopefully not, because we are dealing with them accounting as well, that would be something to look at before next time. But what we're going to be dealing with is we're going to be dealing with relations, which are the sort of foundation precursors to functions, and they're going to be built from some sort of subset of cross products. Okay? But that's it for today. That does wrap up everything humanly possible. Not really, there are more stuff you can do with counting, but that wraps up all of the stuff that we're going to be doing with counting. So I'll hang out if you guys have any questions, but otherwise we are done.